Intro to Algebra, Lesson 1-2B. We've been spending some time evaluating different expressions, and in order to evaluate anything that's more complicated, we have to make sure that we understand some different symbology and order of operations types of things. So to begin with, let's talk a little bit more in depth about grouping symbols. Grouping symbols can be parentheses, which I've shown here in red. They're usually kind of round. And they could be brackets, which are similar to parentheses, except they have sort of a top and bottom little foot that sticks out. Or they could even be the division line, which separates the top from the bottom. And I've given some examples of each one. Here's an example of using parentheses in a problem. Those would be grouping symbols. Here's an example of using brackets. So again, these would be the brackets right here. And if I use the division symbol, separating the top from the bottom, then here's the line for the division sign. There's the top, and there's the bottom. And you could incorporate all three of these together. It's possible that I could have some parentheses here, and I could also put some brackets there. Right? So all three of them could be working together. I might even put the brackets around some parentheses, or even get crazier than that with parentheses like so. I mean, there's a whole lot of variations how they could get mixed and matched, but the idea is you want to be able to recognize all three, parentheses, brackets, and the division line, as potential grouping symbols. According to our order of operations, these grouping symbols are what should take place first. Everything inside them needs to happen first. So regardless of what's outside, I would have to do 6 plus 3 minus 3 first. 6 plus 3, 9. 9 minus 3 is 6. That would take place first. Then I would move outside the parentheses and finish the order of operations. Now, evaluating expressions when we're given variables, again we use the substitution property, and we will replace any variable, in this case t, that we see with a 2. Any variable r with a 3. And then we can go ahead and follow the order of operations. So here we have a relatively easy one. We will substitute the 2 in for t and the 3 in for r, leaving us with 2 plus 3 squared. Now we do not want to take this 2, this square, and give it to each of these numbers. We want to do everything in parentheses first, because that's the order of operations. So 2 plus 3 would then equal 5 squared. And we know that that's not 5 times 2. That's the base number with the exponent of 2 telling us how many times the base should multiply together, which would be 5 times 5, which is 25. So given the values of t equals 2 and r equals 3, this expression has a value of 25. We change these variables, change their values, we change the value over there. Alright, another one. Again, t is still equal to 2 and r equals 3. So now we have 2 squared plus 3 squared. Now some people will say, well, that's going to give the same answer because you had t plus r, and they're both being squared. Well, maybe, we'll see, we'll find out. 2 squared is 4, 3 squared is 9. I'd say 13 is a different answer than 25. So as I mentioned before, if you have the 2 on the outside with addition here, do not give each of them that square. That's essentially what this was. It will produce a different answer. Alright, a little more evaluating. Evaluate the expression when c is equal to 3. So this time, we have some exponents, but we also have some multiplication, because we do not see an operation sign right here, which means that's 3 times c to the third power. So we will substitute this 3 right here, giving us 3 times 3 to the third. Now, according to the order of operations, I don't want to do multiplication first. In this case, I must take care of the exponents. 3 to the third means I'm going to have 3 times 3 times 3 times 3. Now, I'm going to rewrite these 3 with a different color, just so you can see them. These 3 right here are from this. This green 3 is from right here. Now, it really isn't going to matter now because it's all multiplication. One way you could do this in your head is you could say to yourself, well, that right there is 9, and this right here is also 9, and 9 times 9 equals 81. So So if we evaluate this expression, we put the 3 in, 3 to the third power, 3 times 3 times 3 is going to equal 27, multiplied by this leftover 3, and we'd end up with 81. Had this not been a 3, if this was like a 4 or it was a 10, then I would still want to do these exponents first, and then multiply my answer by whatever was left out. Alright, here we again have a C value of 3. Now this is a little different, because there's some parentheses involved. I must take care of whatever's inside the parentheses first, then when I'm done with those parentheses, I'll then use the exponent. A little different. Up here, no parentheses. So I was doing the exponent first. Now this parentheses, got to do the grouping symbol first. 3 times 3 to the third. Probably won't produce the exact same answer. This time, we have 3 times 3, which equals 9 to the third, which means 9 times 9 times 9. Alright? 9 times 9 is 81. Then times another 9, we would probably take the 81 and make it an 80 and a 1. If we can, we'll multiply that 9 times the 80. Well, 9 times 8 is 72, so 9 times 80 is 720. Then 9 times the other 1 is 9. Put them together, 729. Again, quite a big difference. When we didn't have parentheses, we were taking the 3 to the third power, which didn't make it quite as large. Here we multiplied first, which actually made the base much larger. Here the base was only 3, here the base was 9. That's why it got so much bigger when we took the 3 into account. Alright, a couple different shapes. In this case, we have a square. And on a square, all the sides are equal in length. That's why I just wrote S for side. So we could come up with a formula for the area. Probably the biggest mistake that's made for area is people mix it up with perimeter. And they come up with, oh, there's S and S and S and S. That means there's 4 S's. But in reality, we really want to take this side times that side, which means we have S, different color, S times S. And anytime they have the same base being multiplied, you really know that that means the area equals S squared. So any area of a square is going to be S to the second power, or S squared. It's what shape? We refer to that as squared. Interesting. Volume. Volume usually says, in this case this is a cube, and I know it's a cube because the length, the width, and the height, they're all the same value. And no matter what, if we take the volume of a rectangular prism, which a cube is a family of, we would take length times width times height, or side times side times side, which gives us V equals side times side times side. Again, you have the same base being multiplied by itself 3 times, which means V equals S to the third power. And what shape is this? This is a cube, which is why we refer to anything that's to the third power as being cubed. So I ask, is there any connection with the names of the shapes and the area or the volume? Yes, absolutely. This is a power of 2, which refers to this shape right here being a square. That's why whenever we see a power of 2, we can say it's squared. This is a 3, referring to the cube. That's why anytime we see a 3 for an exponent, we can refer to it as being cubed, because those 3 dimensions would make a cube, which is a 3-dimensional object. When you go to the movie, it's a 2-dimensional object. It has the width and it has the height, only 2 dimensions. When the movie comes at you, you go to a 3D movie. That D stands for dimensions, 3 dimensions. It now has the same length, it has the same height, but it has width because it's now coming at you, or depth. In our last example, what is the area of a square with side lengths of 6? One of the best things you can do is get a diagram. So here's my square, side lengths of 6. But we're looking for the area. We said that the area was the side squared, which means, in this case, it's going to be A equals 6 squared. And 6 squared equals 36. So we would say 36. Now I didn't say what the units were. Inches, meters, feet, miles. So we would say UN for units squared. This particular shape is 36 units squared. If it's meters, great. It's 36 meters squared. If it's feet, then it's 36 feet squared. You can multiply the units the same way. Since that's 6 feet times 6 feet, 6 times 6 is 36, feet times feet would be feet squared. And one for volume. Again, sometimes it helps to have the shape. So I can quickly draw one here. And I'll just connect it freehand, make it a little quicker. Okay, there's our cube. It says that has a volume. We want to find the volume of the cube with side lengths of 4. So that means there's a 4, the width is 4, and the height is 4. We gave the volume formula as side cubed. In this case, that's 4 cubed. Do not say 4 to the third power is equal to 12. That means 4 times 4 times 4, which equals 64. In this case, it's not units squared. This is a what dimensional object? A 3-dimensional object. It will be units cubed. If it were feet, it would be 64 feet cubed. 4 feet times 4 feet times 4 feet. Feet times feet times feet would be feet cubed. And it would mean that there would be 64 little cubic feet stacked inside there to fill up this entire volume.